Thank you very much, Aditya, and thank you very much for inviting me to come and speak today. Very excited to be here. I think the topic is going to be slightly more high-level discussions, so not so math heavy, although the previous talk was super interesting. So I've only got 15 minutes, so I'm going to jump straight in. Is my slide sharing okay?
Yes, it's perfect.
Okay, perfect. So as Aditya mentioned, my name is Peter. I'm the head of data science at Monolith. We are a London-based startup, and we have a cloud platform that allows engineers to exploit AI as part of their engineering workflow, with the eventual goal of designing optimal products faster and saving them time as part of their engineering workflows. The platform itself is very intuitive to use. It's no code. It integrates with a number of different engineering tools. And the idea is it's very intuitive notebook style interface. So low barrier of entry for people who perhaps don't have skills in Python programming or that kind of thing. So in terms of where we segment our AI capabilities, we tend to work across the entire product lifecycle, from design, simulation, through to physical test. And we generally find that the data availability tends to increase as you move further towards the right-hand side. And then in terms of areas where we are applying AI, I think generally things kind of get segmented into 3 different types of use cases, starting from simple understanding, exploratory design analysis to kind of relate design variables, figure out which of your design variables can actually be ignored, which ones are really important, and where to concentrate efforts. And then stepping on from that, being able to predict the outcome of using AI to basically predict the outcome of design changes on the real world performance of a particular product. And then at the end of the day, most engineering companies care about being able to find optimal design configurations that fit the constraints and performance criteria that they require. So we work with a lot of automotive, aerospace, and manufacturing companies in order to help them exploit AI as part of their workflow. So we have a number of algorithms that operate directly on 3D data. So we're a big fan of autoencoders, which I think, based on the audience here, you guys will be very familiar with this type of technology. And autoencoders are a really powerful technique for engineering because they effectively act as a complexity reduction mechanism, which, when you have a very high dimensional input like a 3D geometry, reducing the complexity can be really important. So, I mean, I'm sure everyone understands all of this, but the autoencoder is effectively a type of neural network where the data is passed through the input of the network through the network layers, and the network attempts to effectively recover the original geometries at the end of the network. And a key element of the autoencoder is this information bottleneck, or this latent space, which is kind of expressed in green in this diagram here. And typically this has a smaller number of variables than the input. And this compressed section of the network is what helps the model keep only the most useful information that abstracts the geometric features in a much smaller dimensional representation. So it's kind of like PCA on steroids, if you like, where PCA tends to focus on a linear subspace. Autoencoders are able to map much more complex nonlinear relationships into a lower dimensional subspace. And you can also stack them. So you can train an autoencoder to map a particular latent space, but then you can train a secondary autoencoder on top of that latent space to create a stacked autoencoder. And we found that to be a particularly useful pattern for certain types of engineering problems. So why do we want to do auto encoding? What's it useful for? So design simulation technologies are really well developed and ubiquitous. Having said that, the early conceptual design phases are still limited, and human experience and learned experience over decades of engineering expertise still play a critical role in establishing the design space and the associated parameterizations. In the cases where the form and the geometry of the product has a significant impact on performance, then exploring the design space can be particularly challenging. And because of this, the need for tools that can support historic knowledge extraction from different past designs can be really useful. And the beauty of things like autoencoders is they can be used to serve multiple different downstream tasks. So I've listed out 3 here that we commonly work with different engineering companies. So the first one is generation. So as I mentioned, the autoencoder is capable of extracting features differently from a human perspective and enabling a different kind of geometric parameterization and the generation of novel designs that wouldn't typically be created by a human. Second use case is around prediction. So this approach is around learning a direct mapping from available past designs to perhaps their performance. And the reason why this is useful is it can effectively act as a cheap simulator to evaluate new designs in the future. The third one, which we've already touched on, is optimization. So this is typically a pattern that we use when the dimensionality of the design space can be particularly large, making optimization particularly challenging. So approaching this by first doing a dimensionality reduction with an autoencoder can make the optimization much more tractable and complete in a much more reasonable time. So to talk a bit more about a specific use case, as I mentioned, we work a lot with automotive companies, and one of the big problem statements for them is about developing products in as quick a time as possible. And so for them, what they would really like to achieve is being able to predict potential performance of, for example, a new wheel design very quickly, and have a platform that supports their team in understanding the connections between those designs and the performance to facilitate decision-making. So one of the ways in which we can approach this kind of problem is we can take the 3D data as input, and we can also take the performance data from the FEA simulations. For example, here we could be looking at max bending stress. So in this case, we might be looking at stress and fatigue testing of a rim. The customer comes with designs and they want to know if it will work in different driving conditions, hitting a curb, severe load, and maneuver conditions. And so we want to relate sort of the max bending stress to the geometric data. So as part of the input, we would have the collection of rims. We would pass it through first a voxelizer, because that's the particular tool that we have in the platform. We would then encode it twice to get a secondary latent representation, combine that with a performance data from simulations, and then fit a classical or a neural network type model to that in order to predict the performance. And the output of that is that we are then able to sort of use that model to predict the performance of new designs. So inside the platform, we can load new design configurations. They can get encoded in the background, and we can see real-time predictions for performance of those designs. Okay, so the second part of that particular use case was about understanding. And this is kind of what leads me on to the second part of the presentation, which is all around explainable AI. One of the big challenges with neural network models, which I'm sure everyone here is quite aware of, is their black box nature, and the fact that it's hard to unpick how the decisions are being made. And as AI becomes more advanced, there's a real challenge to figure out how the algorithm comes to a specific result. So explainable AI is really a set of processes and methods that allow human users to try and comprehend and understand the outputs being made for machine learning algorithms. So the question is, how do we apply this kind of technology to these autoencoder type solutions, and are they needed? Well, is explainability in AI needed for engineering? Well, I think the answer is yes. But if you think about it, the need for explainable algorithms really depends on the cost of making a wrong decision. And when you're talking about stress of an aircraft wing under turbulence, or critical part of manufacturing of a car, then the risks are such that robustness and trustworthiness are really important characteristics for engineers. So the other aspect is explainability can help engineers to trust and understand what the model is saying. So is it lining up with their decades of engineering experience and their physics-based models? So in a sense, marrying together the AI with the subject matter experts. And it's a way of being able to also justify the particular decisions being made by the model. Model performance plateaus is another thing that explainability can help with. So if you're in a situation where you've done as many hyperparameter optimizations as you can, and you're not sure how you can move forward in improving your model, perhaps explainability can facilitate direction for where more data could be collected, or where parts of the system are not as accurate as they could be. So I'm going to talk about sort of one technique. We have used inspiration from the kind of 2D world, which has been getting a fair bit of attention at the moment. So when we talk about image classification, you can see this example of an image being classified as a dog. Then 2D saliency maps provide a nice way of justifying how the model has come to the decision it's made. So the natural question is sort of, how do we apply those techniques to the 3D world? And one of the ways we can do that is we can make use of gradient information in the model, which is actually really handy for neural networks, because we end up computing gradients as part of the backprop anyway to learn the parameters of the model. So we can make use of that. And effectively, explainability is really, for some trained model and some output, we're interested in calculating the impact of a particular input feature for the prediction. So in the case of the dog classification, an input might be a pixel. In the case of a 3D geometry, or if it's in the form of a point cloud, then the input can take the form of an individual point on the geometry. And thereby the 3D saliency map is a kind of surface on top of the geometry, which is telling you which parts of the geometry are affecting, in this case, the drag of the vehicle the most. So the idea is that the gradient tells us the importance of a particular dimension, and the input tells us how strongly this dimension is expressed in the 3D object. One particular challenge with gradient-based approaches is it's very local information. So when you're explaining complex functions, the gradient can change very quickly, even after a small change in input space. So that may mean that the function goes up if we take a small step in the gradient direction, but if we keep continuing, then it may actually go down more if we continue in the same direction. So I've got about 1 minute left. So just to summarize, where can explainability tools like this add value to engineering workflows? I think accelerating design understanding, identifying parts of the geometry which are responsible performance. This is much harder to achieve with non-parametric design. showing that certain areas of the design are very sensitive to performance is really helpful for decision making. It can also help with design of experiments. So really focusing attention in areas which are likely to maximize changes in performance as opposed to highly linear regions, which are less interesting and less testing needs to be required there. The other aspect is being able to take into account manufacturability early in the design phase. Important design decisions are being made fairly early in the conceptual design phase. And this tends to be a time of very low information availability. So being able to actually justify these decisions based on historic data, rather than sort of anecdotal or rules that perhaps can sometimes contradict each other, can only be a good thing. The other aspect of these explainability techniques is they complement things like complex sensitivity maps, which can be created, which are an extremely expensive approach, whereas using the model provides a sort of cheap option to get similar results and effectively reduce time and iterative loops between design and simulation engineers. I think I'm out of time, so I will say thank you very much, and I'm happy to take any questions now.